Hello everyone, my name is Celine Lee. Today I'm going to talk about a mesoscopic morphologies in frustrated ABCbottolebrush Block Terpolymers for my TM project. So this is the outline for my talks today. First, I'm going to talk about the author, and then I'll go on to the introductions, and then results and discussion, finally the conclusions. So now, let's talk about the author. Professor Bates is a Regents Professor in the Department of Chemical Engineering and Material Science at the University of Minnesota. He earned his bachelor degree in mathematics from the University of Albany and master degree and doctor degrees in chemical engineering from MIT. From 1982 to 1989, he was a member of the technical staff at AT&T Bell Laboratories before joining the University of Minnesota, where he later served as department head from 1999 to 2014. Professor Bates is a member of the U.S. National Academy of Engineering, the National Academy of Sciences, the American Academy of Arts and Sciences, and the National Academy of Inventors. His research focuses on polymers, including the thermodynamics, dynamics, structure, and properties of block polymers, blends, and solutions. He has published over 550 articles in leading peer-reviewed journals, contributed to several commercial products, and co-founded Valerian Materials in 2015 to pursue sustainable plastics. Throughout his career, he has mentored over 100 PhD students and 50 postdoc fellows, and has been honored by the American Physical Society, American Chemical Society, American Institute of Chemical Engineers, and the Materials Research Society for his outstanding contributions. Now, let's talk about the introduction. Let's begin by discussing what a bottolebrush block polymer is. Bottolebrush block polymer is a macromolecular characterized by densely grafted side chains along a backbone, which enables it to self-assemble into large tunable nanostructures. It merges the principle of block copolymer chemistry with a unique bottolebrush molecular architecture. While traditional AB diblock bottolebrush polymers generally form only simple lamella or cylindrical faces, their structural diversity is limited. In this study, Professor Bates and his team synthesized a library of 50 ABC triblock bottolebrush polymers, which is PIA, PEP, and PS, using ring opening metathesis polymerization. They intentionally designed a frustrated system where the internal interfaces, which is PIA, PEP, and PEP, PS, exhibit higher interfacial energies than the PLA-PS interface, promoting the formation of more complex morphologies. Since this project is part of a course focused on TEM, I will particularly emphasize the TEM characterizations, methods, and findings in the following discussion. Now, let's talk about results and discussion. Here, the mechanism for synthesizing the frustrated PIA, PEP, PS bottolebrush block terpolymers is shown. However, due to the time constraints, I will skip over the details of the synthesizations for now. Okay, now let's move on to the phase behavior of the ABCbottolebrush triblock terpolymers. The bulk morphologies were primarily characterized by small angle X-ray scattering, with additional analysis by transmission electron microscopy. Oh, and by the way, polymer samples were freeze-dried and annealed at 150 Celsius, well above the glass transition temperature of all blocks, under vacuum for 24 hours. ACS measurements were conducted at 80 Celsius after a 10 minutes equilibration. For TEM, ultra-thin section around 70 nanometers were prepared by cryomicrotoming at around -70 Celsius and exposed to vapor from an aqueous ruthenium tetroxide solution for 4 minutes. So this staining method produced strong contrast. So here, the PEP domains appeared white, and PLA domains appeared light gray, and PS domains black, enabling clear morphological visualizations. So here, the LAM phase was identified by the appearance of sharp diffraction peaks in the SAXS patterns. SAXS analysis of other layered structure, which is, for example, like DLAM, LAYM, and 2LAM, also revealed lamella-like peaks, along with additional typically broader peaks. All layered structure identified through SAXS were further confirmed by TEM imaging. These layer structure were prevalent in the low molecular weight PLA, PEP, and PS, bottolebrush block terpolymers. Pure layer phases were observed in both the low FPS, which is lower than 0.11, and high FPS, which is higher than 0.35 regions, while the medium FPS range between 0.11 to 0.35 showed a coexistence of cylinder containing morphologies and layer phases. Now let's look on the core shell hexagonally packed cylinders, which is short for CSHEX. So a core shell variant of the HEX phase was observed in the PLA-rich region, specifically within 0.5 for FPLA to 0.6, and for FPEP is between 0.16 to 0.34 and 0.13 to 0.24 for FPS. This phase coexisted with LAM structures. As shown in the TM images, white PEP domains form the shells surrounding black PS cylinders, all embedded within the gray PLA matrix. And also in this figure, we can see that there are some distortion of the unit cell from perfect hexagonal symmetry was noted, likely caused by either oblique slicing during microtoming or shear deformation during sample preparation. Now let's move on to alternating tetragonally packed cylinders, which we short for ATET. And in figure 6A, it shows the SAXS pattern exhibiting P4mm symmetry, while the corresponding TEM image for 6B confirms the presence of alternating tetragonally packed cylinders. In this structure, PLA and PS form the gray and black cylinders, respectively, while PEP serves as the white matrix. This tetragonal phase appears primarily in the PEP-rich region within the composition range of 0.22 to 0.34 for FPLA, 0.32 to 0.58 for FPEP, and 0.14 to 0.35 for FPS. And let's talk about rectangular center cylinders in undulating lamella, which is RCCUL. So here, an extraordinary RCCUL phase with C2mm symmetry was observed in the region where FPLA similarly equal to FPEP. And the region for FPLA is 0.34 to 0.49, for FPEP is 0.31 to 0.52, and 0.11 to 0.2 for FPS, positioned between CSHEX and ATET phases. By combining SAXS indexing and TM imaging, the RCCUL phase was characterized with unit cell parameters where A similarly equal to B, similar to the TM image of CSHEX. A slight deviation from 90 degrees in the unit cell angle was noted. It is likely due to the oblique slicing during cryomicrotoming or deformation during sample preparation, like we mentioned before. And in figure 7B, the black cylinders correspond to PS domains, and the undulating gray layers represent PLA domains, and both are embedded within the white PEP matrix. Finally, let's talk about the giant RCCUL phase they discovered. So they targeted the RCCUL composition region and increased the total molecular weight of the bottolebrush polymer. And here in figure 8, It presents the SAXS pattern and TM image of a high molecular weight of RCCUL sample with unit cell parameters of A equal B and equals 62.8 nanometer. Unlike the low molecular weight specimen, which showed a minority LM phase, the higher molecular weight sample exhibit a pure RCCUL phase. In the TEM image, narrow light gray stripes within broader bands and an increased volume fraction of black cylindrical domains suggest that ruthenium tetroxide staining may have selectively highlighted the block interfaces rather than staining only the PS domains. Okay, finally, let's talk about the conclusion of the study. So in these studies, the authors synthesized a series of frustrated PIAPEPPS bottolebrush block terpolymers with varying compositions and molecular weights using ring opening metathesis polymerization. Morphological characterization by SAXS and TEM revealed several mesoscopic structures, including core shell hexagonally packed cylinders, CSHEX, alternating tetragonally packed cylinders, ATET, and a newly discovered phase rectangular centered cylinders in undulating lamella, RCCUL. Increasing the molecular weight led to giant RCCUL unit cell dimensions up to 130 nanometer, much larger than those in linear polymer systems. These results highlight the structural diversity and tunable dimensions of ABCbottolebrush Block Terpolymers, expanding their potential applications in photonics, nanofabrication, and membrane technologies. Thank you for your attention.